In this series of videos, we're going to explore what exactly is meant by a chemical reaction and what is it that makes atoms more or less able to react with one another. Now, before we begin, we need kind of a dictionary definition of what is meant by a chemical reaction. So we can say that a chemical reaction has occurred when two elements feature an exchange of electrons in their valence shell. And remember that valence shell, or an element's valence shell, is the shell of electrons that is outermost from the nucleus, meaning that the valence electrons are farther away from the nucleus than any other electrons that element has. And after this exchange has occurred, this means that we now have a compound that was not present before. Now, the example reaction that we're going to be looking at involves probably a substance that everyone watching this video has encountered in their life, NaCl, that being plain old ordinary table salt. So if we look at the way that this reaction occurs, we need to look at the valence shells of sodium and chlorine. So we can see from its Lewis structure that only shows the valence electrons that sodium has one valence electron, whereas chlorine has 7. Now, the important thing to consider is that the maximum number of valence electrons for both sodium and chlorine, that being any element with a second or third electron shell, is a total of 8. This is what we refer to as the octet, as we've talked about in previous videos. Now, if we look at how each element is more easily able to attain an octet, we can start with sodium. Now, remember that the total is 8, so for sodium, losing its one electron, giving its one valence electron away, is much easier than having to gain 7 additional electrons, because it involves only the movement of one electron as opposed to 7. And for this reason, sodium, like pretty much every metal, is more easily able to lose its valence electron than it is to gain. Whereas with chlorine, because it already has 7 valence electrons, the exact opposite situation is true, where for chlorine, gaining one electron, in this case gaining it from sodium, is much easier than losing its 7 electrons that it already has, because it simply involves the movement of a single electron. And for that reason, chlorine, like most other nonmetals, is more easily able to gain electrons than it is to lose electrons the way that a metal like sodium is. And if we rewrite each of the two Lewis structures, as we can see below, showing that sodium has lost its one valence electron for a full valence shell, therefore gaining a positive charge, whereas chlorine has gained one additional electron from sodium for the addition of a negative charge, we can see that this is how, not just how individual metal and non-metal ions form, but actually how the two ions come together in order to form an ionic compound. And this basic idea of the metal losing its valence electrons while the non-metal gains additional valence electrons is basically how all ionic compounds form. However, as we can see below, this type of valence electron exchange does not exactly occur when we are dealing with two nonmetals forming a compound. So, for example, we can see that both hydrogen and carbon are nonmetals, so we're not going to get the same type of one element loses and one element gains as we saw with an ionic compound. So instead of one nonmetal losing electrons and one nonmetal gaining electrons, we can see that hydrogen and carbon do something a little bit differently. And the explanation for that we can see easily by looking at each element's valence electrons. So hydrogen is a little bit unusual for most elements because hydrogen only has a first electron shell, which has a maximum of 2 electrons, and of course hydrogen starts with 1. So this means that hydrogen can either gain 1 electron or it can lose one electron. Now, if a science teacher asks you which is easier, gaining one or losing one, this is actually a trick question because both of them are approximately equal to do. So this presents hydrogen with a little bit of a problem, which carbon also has as well. So remember, with carbon, because it has electrons in its second shell, the maximum number of electrons that carbon can have is 8 in its valence shell, and that means that carbon can either lose or gain 4 electrons, and just like with hydrogen, it is basically equally easy for carbon to lose 4 as it is to gain 4. And so neither element actually does either, but they opt for a compromise solution where they share electrons instead. So basically what happens here is that because hydrogen and carbon basically want electrons equally as each other, they decide to form 4 pairs of electrons like this, which inevitably involves both hydrogen and carbon sharing their electrons in order to form different types of structures that are not found in ionic compounds. So here we can see the Lewis structure of a compound formed between hydrogen and carbon. So electrons that are shared in this type of Lewis structure, we don't write them as 2 dots. Instead, we represent them as lines like this. So this line here represents 2 electrons, one from hydrogen and one from carbon. This line represents these 2 electrons, and so on for the rest of these electron pairs. And because these are not transferred from hydrogen to carbon or vice versa, we don't refer to them as electron pairs in the traditional sense. Instead, we call them what we call covalent bonds. And the name covalent actually tells us a little bit about how these electrons are shared. So from the English prefix co, which means with or together, and valent obviously refers to valence electrons, we can see that these 2 electrons exist in the valence shell, in the outermost electron shell of both hydrogen and carbon, meaning that together each of these pairs form the valence shells of each of the 2 elements that form the bonds. And this is predominantly how nonmetals form compounds with each other, by sharing and forming covalent bonds rather than a direct electron transfer that we see between metals and nonmetals, which is how ionic compounds form. In the next video in this series, we're going to look into how to predict whether an element is more likely or less likely to react with other elements and form compounds, specifically by looking at the number of valence electrons that given elements have.